all, before I even go on, I really need to acknowledge all the people that have put a great amount of effort into this work. Mika Webtolainen, who was my colleague at CSIRO, who's an actual electrochemist. So if there are any technical problems with this work, give Mika a call. And then there's Leanne Smith, who hopefully did the flotation test work back at CSIRO, and Colin McRae, who did some of the characterization work. So, let's get to the background. What is pyrite? Pyrite, if you Google it, it'll tell you that it's fool's gold and it has long been valued as a strong protection stone that shields the weather from negative energy, stimulating the second and third chakras, whatever those are, and pyrite enhances strength of mind and willpower. So it sounds incredibly hopeful. We should all have pyrite in our lives. But for all those of us who are a bit more technically minded, it is a very common sulfide gang in base metal sulfide processing. It is also a valuable mineral if you want to recover gold or platinum group metals that occur in association with pyrite. And there are a great many different types. In fact, probably more times than we know about, ranging from the beautiful, pure, blocky, pretty stuff that the crystal people go crazy about with their chakras and willpowers, not to offend any of them, they're all great people. But also going to the really strange carbonaceal rhomboidal pyrites. So there's quite a gamut of them. So in particular, here at the JK, there was a lot of work conducted on pyrite in the context of Newcrest Lihir gold mine. So this is data from Joseph John's PhD, where he looked at pyrites with different textures. So there was the really nice, smooth, blocky pyrite, going on from dihedral resorbed zone laminated. All of these have very visually strong textural differences, which were used to identify them. So you could say, right, this pyrite, resorbed pyrite, has certain chemical characteristics, and we can identify it by looking at its texture. So there are many, many different types of pyrite. Abratus in 2004 did a very exhaustive review and found 11 different types of pyrites. Doyle and Mirza did electroactivity surveys of pyrite and looked at 12 different types. And so what Abratus found is that you have a huge variation. You have some minor elements, including gold and arsenic, as well as a great number of trace elements such as silver, stibnite, bismuth, etc. What was found is that there is a very, very strong link between the presence of arsenic in the pyrite and the presence of gold. So if you are looking for gold and can't find it, look for arsenic, and you will likely find gold there. That's a very strong link. Another very strong link was found between the presence of arsenic and the level of electroactivity of that pyrite. So, what is pyroelectroactivity? What does that mean? Well, electrochemical activity is defined as an affinity of a substance, in this case a mineral, to either receive or donate an electron to another substance, another mineral, or an electrolyte-rich medium, flotation or grinding medium, for example. So, when interacting with an aqueous medium, in the presence of oxygen, this means that mineral surfaces tend to oxidize. When the interaction between two minerals, it leads to a galvanic interaction. So this is a table from Abratus, which gives you the rest potentials, which are indicative of electrochemical activity of a number of really common base metal sulfides that we deal with pretty much every day in mineral processing, and pyrite sits right at the top. It is one of the most electrochemically active minerals that we deal with in base metals altogether. So what are galvanic interactions? Chris Great, who was here last week, did a beautiful overview of all of this, and I will not try to match it. However, to those of you who weren't there last week, which is a very quick overview, it is a flow of electrons from one substance to another, accelerating the oxidation of a mineral pair or a triplet in an aqueous interface. It occurs through direct contact, as well as indirectly through a medium, although the interaction is much stronger with direct contact. The mineral behavior is not of a mineral is not the same individually as it is when present in a galvanic couple. And this is a primary reason why when we do tests on single mineral systems, when we then try and replicate the result in mixed mineral systems, it does not behave the same way. This is a primary reason why so many scientific studies have misinterpreted to mean that when a mineral behaves on its own in a certain way, it will continue to behave in the same way when placed in a mixture or present in a composite mineral protocol. This is hugely important and cannot be understated. So, how does that affect floatability? Well, floatability is an interesting beast. Began last week with Chris Reed's talk. He talks about, well, we want to prevent oxidation because oxidation means corrosion, means you're destroying the activity of all your surfaces. To an extent, that's true, but that's not all the truth to it. Oxidation can be your friend. So what happens? Initially, when your pole potential is very low and you have completely reducing condition and no oxidation takes place, none of the minerals exhibit any floatability at all. And then as you progress to slowly more oxidizing conditions, the floatability sharply rises, reaches a peak, and then drops off like a rock. And this behavior is different for every different mineral type. Mind you, these were done individually and not with mixed couples, so you will not expect the exact replica of this behavior in a real system. But this difference is there because of the difference in the chemical activity of each of these minerals. So why does that happen? What is the mechanism behind all this? Well, it's actually quite simple. When you have no oxidation happening, all you have is a metal surface. You have metal ions present on the surface. Those don't float on their own, they are hydrophilic. However, some collector species can react with them, giving them a modicum of floatability. When oxidation initially kicks in, the first thing that happens is you have elemental sulfur being deposited in the mineral surfaces. Elemental sulfur is completely water insoluble, so it forms this beautiful, completely hydrophobic layer on the mineral surfaces. Things float like crazy in the absence of collector, but sulfur also reacts well with collector, which further boosts the floatability. So this corresponds to this lovely peak right here. As you continue to oxidize further, you start to form metal sulfoxy species on the surface. So you have a bit of oxygen being mixed in the system. Sulfoxy species are moderately water soluble, so they're not, when you have them on the surface, the hydrophobicity starts to drop off, they interact a bit more with water, but they interact beautifully with collectors. And so as a result, in the presence of collector, we have really high floatability. We have here. But as you progress further and further and further, in the end, all you're left with is metal hydroxide species left on the surface. Everything's oxidizing. Metal hydroxides are extremely water soluble. They completely dissolve in water. They form this completely hydrated layer on the mineral surfaces, and nothing sticks to bubble anymore. There are, however, a few rare collector species, when present in very high dosages, can interact with hydroxide species to a limited degree. So you can still get a low level of floatability in the presence of future quantities of collector. And essentially, this is flotation chemistry 101. This is how it all works. So, how do galvanic interactions affect all of this? The video thing is a little bit ill-placed there. This is a very well-studied phenomenon, particularly for interactions between chalcopyrite and pyrite. So the work was done in Hajitepe by Meshi and JKMRC. The work was done at the Future Industries Institute by Clement also, and the work was done at CSIRO by Bill Traer. And ultimately what happens is when you've got chalcopyrite present on its own, in the absence of, in a small quantities of pyrite present, it floats beautifully. Chalcopyrite floats like crazy. But as soon as you start to add more pyrite to the system, floatability of chalcopyrite drops out the wall. It prevents chalcopyrite from floating by merely being present. On the outside, if you have pyrite floating in the presence of chalcopyrite, initially the floatability is relatively good, but then when you have more chalcopyrite in the system, the flotation in fact gets better. So when you have chalcopyrite floating beautifully on its own, pyrite floating poorly on its own, you mix them together, suddenly pyrite floats and chalcopyrite doesn't. Not what you want when you're trying to reject the pyrite. So, why is any of this important? Why are we bothering to sit here and listen to a bunch of chemistry goings on when all you really care about is bubbles in the system? Well, I'll tell you why it's important. Okay, here at UQ and JKMRC, a lot of the focus was specifically on pyrite as the main atom. You either want to reject it because it's organic, or you want to recover it because it's got all the gold or all the PGMs in it. So that's the main focus. But where I came from in CSIRO, we were far more interested in pyrite in the context of separating copper from arsenic. We wanted to have copper concentrates that you could smelt without worrying about arsenic penalties. And in that particular case, pyrite is not center stage. It is a shadowy villain. It is Bruce the Shark lurking the murk, messing up everything without really fully being seen. And so now that I'm here at the JKM, the Complex Ore Bodies program is now also looking at arsenic processing as one of its main foci. It is also coming to the fore. So both of these aspects of pyrite are equally important and really need to be looked at in order to have a successful outcome of processing base metals. So, what is the objective of this particular work? Now, this is where it gets a little bit dry, so I'm going to read it out, so it's all very, very specific. The interactions between pyrite and chalcopyrite are very well studied. We know this. But less information exists about the type of pyrite that is present and how that affects different interactions. So this study, we're looking at properties of different pyrite types and how these properties have affect the surface properties of chalcopyrite through galvanic interactions and how that affects the subsequent behavior in flotation. So this is part of a greater study that focuses on arsenic-bearing minerals and separating them from copper minerals and copper concentrates, and ultimately looking in a very far hypothetical distance. The long-range goal is to put together semi-empirical models of mineral interaction within complex particles with the view of modeling liberated ore systems based on their particle composition. But that's quite a long way off. So, what methods did we use? In this study, I focused on two pyrites. One is a Huanzala pyrite from the Huanzala mine in Peru, which is a lead-zinc deposit. And another one, which is a Renison pyrite from the Renison Bell mine in Tasmania, which is a zinc deposit. I'm only looking at two pyrites here. I have in fact looked at about four. I did not have the time or the resources to fully generate a comprehensive data set for all four of them, so I mainly did some preliminary characterization and picked the two extremes. Now, the technology that I used for this is alternating current scanning electrochemical microscopy. So what I did is, I took mineral samples, so little blocks of chalcopyrite, anagite, and pyrite. I went with anagite because I was going to start looking at it next, but never got around to it. I mounted them in a resin block, and underneath each one of these minerals, I have attached a copper wire with silver epoxy to have a direct conductivity conduit that I could easily take either single measurements or galvanic couples just by connecting the two copper wires together. And so we've got two blocks. The chalcopyrite and anagite samples in there were identical. They came from the same block. But the one contained the Huanzala pyrite, the other one contained the Renison pyrite. All of the surface areas were carefully measured, and all of the electrochemical measurements were normalized through exposed surface area. These blocks then they go into a measurement cuvette where they are placed in solution after being freshly polished, so you have a nice new mineral surface. And all the measurements were done in situ in the same solution that was used to then do the flotation test. So things were consistent across the board. I did open circuit potential measurements, which basically gives you the rest potential of the mineral, as well as electrochemical impedance spectroscopy, which gives you the resistivity or the resistance of the surface to electron translate. So it's a very good proxy for electrochemical activity. And yeah, all results are normalized for surface area. Right. Batch flotation tests were then subsequently performed. I used both binary and ternary mixtures. In the binary mixtures, we had 10% sulfide, 90% quartz as your background inert gang. And in ternary mixtures, 5% pyrite of both types and 5% chalcopyrite, 90% quartz. All tests were done at pH 10 at an air set potential of 280 millivolts and this was just done by aerating the pulp for 5 minutes, but that potential was then maintained throughout the test using chemical additives, so it never varied. And we used no collector because we wanted a nice clean system. So, the results. First, I started off with characterizing the two pyrites. So the Quandala pyrite was literally very smooth. Its texture was remarkable by its absence. So it was literally very smooth. The Renison pyrite had a slightly more pitty texture, but it was subtle. If you looked at these two under an optical microscope, you would not be able to tell the difference. So, when we did the EDS of the pyrite, they were both roughly 52% iron, very similar sulfur contents. Again, the Renison contained a little bit more oxygen, but otherwise they were chemically identical. I also assayed them. I didn't include the results here, but the results were also the same. They were chemically practically identical. So I went to QXRD and said, right, are there any crystalline differences and mineral presence, mineral phase differences? And it told me, well, the Quandala pyrite is mainly pure pyrite. But the Renison pyrite had a bit of quartz and chrysobolite occlusions here and there, but none of these are electrochemically active, so they didn't contribute. And they both had tiny amounts of mica, so no real clues there. And finally, I looked at the lattice characteristics, and this tells you how perfect a crystalline structure is and how much it deviates from the ideal. And they were, again, both exactly the same, and the lattice parameters matched the ideal lattice parameters for pyrite almost exactly. So, nothing. The interesting thing was the texture. What I thought was really interesting is that all of this pitting and all of these textural artifacts all had very prominent 90-degree angles in them. And it didn't occur to me to think of them as fractals until I went to Dion Weatherby's talk a couple of weeks ago. And you can actually see the fractal dimensions, everything being multiplied in 90-degree angle factors, which I thought was really interesting because pyrite is cubic, so 90 degrees are part of the course. So why does this happen? Well, I didn't know it, and when I flagged this up at the Flotation 17 conference to the audience, I got sandbagged. I got told, well, this is likely just bugs eating it on the surface, and why are you bothering with this texture nonsense? Go back and do your homework and get the thing properly analyzed. So I went back and did my homework and got the thing properly analyzed, and I got wonderful results, which I'm going to show you shortly. But I'm coming back to texture, because then I got to the JK and they're telling me, well, pyrites have different textures and you have to look at them texturally. Well, there it is. It's a subtle but definite textural difference. But then I went and I did some microprobe measurements with the great help of Colin McRae. We used the JKMRC Super Probe to do it. And first, excuse me, the iron measurements for the two were very similar, slightly more in the Renison pyrite, same with the sulfur, but the Renison pyrite contains 0.16% arsenic, whereas the Quandala pyrite contains 0.01% arsenic. It's a tenfold difference, but they're all very, very small, so can this really be significant? Well, if you look at what the surface actually looks like, this is Renison pyrite. Again, you see these really big textural differences across the board. You see that the arsenic is distributed, I would say pseudo-randomly, because that's not entirely random, across, with areas that have a much higher versus much lower arsenic content. So on average, it is about 0.16% arsenic. But in specific spots, the actual arsenic speciation went above 1%. So in the brighter spots, this one is much greater. Again, an interesting textual observation. If you look at just the large-scale standard electrical microscope image, you see these 90-degree angles cropping up again, and areas of smooth texture contrasted with areas of rough, slightly pitted texture. And these correspond almost exactly to regions of high and low arsenic, but not a single grain boundary in sight. So, how would this break up if you had to common usage? I have no idea. So this is interesting. clear textural differences, complete absence of grain boundaries. So, what is Arsenian pyrite? Because this is Arsenian pyrite. Normal pyrite is just contains iron and sulfur in its purest and most ideal form, which literally never happens in nature. But it can contain occlusions from other minerals such as arsenopyrite. Now, people often confuse Arsenian pyrite with arsenopyrite. Arsenopyrite naturally contains arsenic as an integral part of its crystal structure, much like chalcopyrite contains copper. Arsenopyrite contains arsenic, about 40% by mass. Arsenopyrite is pyrite with random substitutions of arsenic into its crystal lattice, either for iron or for sulfur, depending on which way the group takes. And it can vary between 0.1% and as high as 9% arsenic, as recorded by apparatus. So let's just sum up. Two pyrites. Gonzalo pyrite, it's sourced from Peru, close to ideal pyrite, probably as close as you're going to get to an ideal pyrite, and it completely lacks features. Renison pyrite is also a blocky pyrite. Sourced from Pyrites, it's an Arsenian pyrite. It has some very interesting textural features. The distribution of arsenic is non-homogeneous but relatively pseudo-random, and no visible grain boundaries between high and low arsenic regions. Now, the important part here is that both of these are blocky pyrites. So if you went back to that original graph from the Lihir pyrites, they would have both fallen into that wonderful clear blocky category, and you would not have been able to distinguish between them. One of them contains significant quantities of arsenic and the other one does not. And as we will see shortly, they also have significantly different behavior. So, first thing that happened is I measured the open circuit potential, which gives me an indication of the rest potential and the baseline electrochemical activity of these minerals, the chalcopyrite and the two pyrites. So I started off with just measuring the potential at rest for 30 minutes. I took an average over the last 10 minutes of the test just to give the system time to equilibrate, and repeated everything in triplicate. I did the measurements on individual minerals as well as in mixed galvanic pairs, where I connected two minerals together and allowed them to interact. So what happened was the natural open circuit potential for chalcopyrite was relatively low. That for Gonzalo pyrite was not much higher but still significant, but quite a bit lower than what we would expect of a pyrite. From the data by apparatus, you expect about 660 millivolts. This one's only about 300. Meanwhile, Renison pyrite, which is, curiously obscured by the image of me, which is far less interesting than that of the pyrite data, is sitting around 600 millivolts, which is far more in line with what you would expect from literature. So immediately you see a very big difference in just the rest potential of the two pyrites, and both of them larger than that of chalcopyrite. So then when you look at the galvanic couples, this is a Gonzalo pyrite. When you couple it with chalcopyrite, its rest potential does not undergo a statistically significant change. So they're both within measurement error. However, when you couple Renison pyrite with chalcopyrite, it significantly shifts. So there is a much greater degree of interaction. So little interaction, a lot of interaction is the moral of this particular story. So then we got a little bit more fancy. What we did is did electrochemical impedance measurements. Now, normally when I see a technique like this that I'm not familiar with, my eyes glaze over and I fall asleep. So I prefer for that not to happen. So let me explain to you how this works. What you have to measure is the level of resistance of a mineral to receiving or donating an electron. So resistance to electron transfer is what you're trying to measure. And this is a system that we've got. We have a mineral surface. It is surrounded by a double electrochemical layer. For those of you who know your geology theory will know what I'm talking about, but suffice to say, more electrons, slightly fewer electrons, less electrons in the bulk solution. That's all you gotta know. So an electron from solution to get to the mineral surface has to first find its way through the bulk solution, then run the gauntlet first the first layer, then the second layer, and finally break through to the surface. Because this is our system, we can now put together what is called an equivalent circuit diagram. So we model our mineral as an electrical circuit. And because we've got the electrotransfer resistance component, the double layer capacitance component, and the resistance of the bulk electrolyte component, we put them in a circuit that looks like this. Again, if you have any questions about the veracity of this, please take it up with Miko. And then you plug this equation into some fancy software and it gives you an actual mathematical equivalent of what that looks like. Presumably some people can do this from first principle. I am not one of those people. Then what you do is you perform a measurement where your electrochemical microscope bombards your surface with different frequencies of potential. Exactly how it works I'm not entirely sure, but then you can plot the outcome of the real component of the output versus the imaginary component of the output in what is called the Newcrest plot. Some of you may remember from mathematics, and it gives you this fairly round, semicircular measurement. Now, what a lot of people do, the trap a lot of people fall into is say, right, we've done the measurement. They go to all the buying software and they select the circuit diagram and hence they model the best fits their dot. They go through all of these things, adding more and more fancy components. And it says, right, I've got a beautiful fit, which means that my system looks like this. I've got all these resistances and capacitances all hooked up in strange configurations, and this is therefore my system. That is backwards. Anyone who's ever done any modeling will tell you that that's completely backwards, and it's a really, really serious error. You have to kind of cop the fact that your system is the system. You model it from first principles, and if it doesn't fit your data, you do more repeats and you cop the high error bars. It's just kind of how it is. So, this is why I have high error bars on my data. So what I did is I conducted the in situ measurements in solution. The surfaces, once again, were freshly polished each time, and the surfaces were conditioned at the same open circuit potential that I measured earlier as the rest potential. So things were always kept consistent. The tests were repeated 6 times because I had a lot of variability, with some very, very clear differences between the two pyrites. So here, the resistance to electron transfer, the higher it is, the less your mineral is likely to react. So Chalcopyrite has a relatively high resistance compared to the rest of the minerals, so it doesn't want to react. And then you've got the Chalcopyrite when mixed with a Pyrite, the resistance drops, so it becomes a lot more likely to react with something. And then when present with Renison Pyrite, it drops even further and it becomes a lot more likely to interact with something, either solution or another mineral. When you look at the pyrites themselves, the Pyrite is initially, lower than that of Chalcopyrite, but it's still relatively high. When mixed with Chalcopyrite, its reactivity goes down. You expect it to go up because we know that pyrite flows better when in presence of Chalcopyrite, but this one's going down. So that was a little bit strange. Whereas the Renison pyrite resistivity was very low, down very close to 0, and because of the high variations, I couldn't actually tell whether the couple with Chalcopyrite was higher or lower. It was entirely within the error range. So that was a bit inconclusive, but I would have expected this to go up, and I would have expected this to go up. So let's see what happens with the flotation data. Flotation data is, well, the red line is Chalcopyrite floats beautifully on its own, we all know this. And then when you float it in the presence of both pyrites, the recovery drops a tiny bit, but because this wasn't properly reproduced because we ran out of money and couldn't do assays, I'm not going to take that as anything conclusive or anything horribly statistically significant. We know that there's a slight change and it's probably downwards, but we won't read too much into it. Interesting part happens here. When you are floating the Pyrite, its natural floatability is very low. So what we expected from previous work is that you mix it with Chalcopyrite, it would get better. But it didn't get better, it got worse. Again, slightly, I don't have enough data to fully say with physical confidence that it does definitely go down by how much, but it did, which mirrors what happened here. We expected this to go up, it went down, and guess what? It was reflected in the flotation process. On the other hand, Renison pyrite hardly floated at all on its own. But when mixed with Chalcopyrite, floatability shot up. And even without proper reproducibility of error bars, you can see that that's real. But I wouldn't try and quantify it in any meaningful way because of no error bars. And so here, I was expecting it to go up. The error was too big to say with certainty, but I would guess that if I was going to go back to do more repeats, I would likely see that going up more. So, what does all of this mean? It means that we've analyzed two types of pyrite from Tasmania and from Peru. Chemically identical, visually almost identical with very subtle textural changes. But one is Arsenian and the other is not. And they have distinctly different electrochemical activity. We saw this in rest potential measurements, in impedance measurements, and in flotation measurements, but to a lesser degree. One of the reasons for that was, well, we didn't use a collector. We might have been able to see a greater level of difference in the presence of collector and with a greater ratio between Chalcopyrite and Pyrite in the system. So, what's happening with Chalcopyrite? Well, Chalcopyrite performance was entirely consistent with literature. If you put in more pyrite, the floatability goes down. We have confirmed what was found by at least 3 other researchers, so yay, we have consistency. We saw this also, not just in floatability, but in rest potential measurements and impedance measurements, all confirmed what we saw in the flotation cell, which is always nice. And it galvanically interacted with different pyrite types to a very different degree. Again, we saw this in rest potential, impedance, and flotation to a lesser degree. However, if we were to increase the proportion of pyrite in our mix, we know that it would dampen the flotation of Chalcopyrite even more. And it may then produce a much more significant difference in Chalcopyrite flotation dampening from the 2 pyrite types. Sadly, this is what happens when you're a bit constrained on resources. When you do this kind of work, you simply run out of money and you can't confirm the findings. You badly need to confirm it. It's very sad. Conclusions. Pyrite is not pyrite. Even when you're dealing with 2 blocky, close to ideal pyrites, they're still very different. And these differences can't be detected using standard analytical techniques. And they can't be detected using optical microscopy very easily, although subtle texture can be a clue. Microscopic arsenic substitutes have a disproportionate effect on the electrochemical activity of the pyrite matrix. And these will increase when interacting galvanically with other minerals. The more pyrite you have in the system, the more pronounced the effect is going to be. And they are going to be even more pronounced when you're dealing with a mineral that is less naturally floatable than Chalcopyrite, specifically anodite. Anodite is the big target of it all that I will get to eventually, and that is an arsenic-bearing copper mineral that is a big enemy out there in copper processing right now because it's a toxic element and cannot be smelted. And with that, thank you very much, and I would like to thank all of the people that have helped me, Matthew Glenn, who did the ECMs, Nathan Webster, who did the XRD, Yehuda, Cameron, and Cheryl, who helped me in the lab. They were wonderful, and I could not have done it without them.